Welcome to The Explainer. Today, we're going right to the edge of what's possible. We're going to explore the hard wall that computation eventually hits and uncover the absolute limits of what computers can, and maybe more importantly, what they can never do.
So let's just kick things off with a massive question. Are there problems that computers can never solve? And I don't mean problems that are just too slow or need a bigger computer. I mean problems that are fundamentally mathematically impossible for any computer now or in the future to ever solve correctly.
Okay, so to really get our heads around this, we need to know that in the world of computing, problems pretty much fall into two big buckets. On one side, you have your decidable problems. For these, we can write a program that's guaranteed to stop and give you a straight yes or no answer. Simple enough. But on the other side, that's where things get weird. We have undecidable problems. And for these, no program can ever be written that's guaranteed to work for every case. The poor thing might just get stuck in an infinite loop, running forever, searching for an answer it can never, ever find.
So how in the world do you prove something is impossible? Well, computer scientists have this really clever trick up their sleeve called a proof by contradiction. Basically, you start by pretending a solution does exist. You say, okay, let's imagine I have a program that can solve this. Then you just follow that logic, step by step, until it backs you into a corner and creates a total paradox, a contradiction so glaring it proves your first assumption had to be dead wrong.
So how do you actually use this to prove that a new problem is impossible? Well, you use the impossibility of an old, famous one as a kind of logical weapon.
The tool for this is called reduction, and it is a brilliant mental judo flip. You take a problem you already know for a fact is unsolvable, we'll call it problem 1, and you show how you can cleverly disguise it as your new problem, problem 2. The logic goes like this. Hey, if I had a magic box that could solve your new problem 2, I could use it to build a machine that solves my old impossible problem 1. And since we know a machine for problem 1 can't exist, well, your magic box for problem 2 must be impossible too. Game over.
And this brings us to an absolutely mind-bending puzzle that perfectly shows this whole idea of undecidability in action. It's called the post-correspondence problem, or PCP. And on the surface, it sounds pretty simple. You've got these dominoes, but instead of dots, they have little strings of letters on the top and bottom. The game is to pick a sequence of these dominoes, you can reuse them all you want, and line them up so that the string of letters you make on the top is the exact same as the string on the bottom. Easy, right?
So for instance, with a certain set of dominoes, maybe we find a solution. We could pick the second domino, then the first one again, and then the third. We lay them all out, and boom! The top string reads BAB 3B3A, and the bottom string also reads BAB 3B3A. It's a perfect match. So for this one specific set of dominoes, we found a solution. Awesome!
But here's the kicker, and it's a huge one. It has been mathematically proven that you cannot write a single computer program that can take any random set of these dominoes and tell you for sure if a solution exists. Sure, it might get lucky and find one, but if it doesn't find one after a billion tries, it can never know for sure if the solution is just one more domino away or if one just doesn't exist at all. It's fundamentally undecidable. And it turns out, even for the problems that we can solve, they're not all the same. They actually exist on a kind of map, a hierarchy of just how complex they are. This brings us to what's called the Chomsky hierarchy. Really, you can just think of it like a ladder of computational power. It sorts problems, or languages, as computer scientists call them, into different levels. And each step you take up the ladder requires a more powerful type of theoretical machine to figure it out.
Way down at the bottom, at type 3, you've got simple, regular problems. These can be solved by a finite automata, which is really just a simple machine with no memory, kind of like a vending machine. Step up to type 2, and you need a push-down automata, which has a basic memory stack, like a stack of plates. You keep climbing, and the problems get more and more complex, until you hit the very top, type 0. This is the realm of the all-powerful Turing machine, a theoretical computer with infinite memory that represents the absolute peak of what's computable.
Okay, so let's shift gears. We've talked about what's truly mathematically impossible. But what about the problems that are technically solvable, but in the real world they're just so ridiculously hard they might as well be impossible?
This lands us right in front of the most famous unsolved question in all of computer science, P versus NP. Problems in class P are considered easy. A computer can find the solution in a reasonable amount of time.
Now, problems in NP are a little different. For these, it might be incredibly hard to find an answer, but if someone hands you a potential solution, it's really fast to check if it's right. Think about a Sudoku puzzle. Solving it from a blank grid is tough, but checking a filled-out grid is a piece of cake. The big question is, are these two classes of problems actually the same thing?
And hiding inside NP, there's this special club of problems called NP Complete. These guys are the absolute heavyweights, the hardest of the hard. And they all share this wild property. In a very real sense, they are all just the same exact problem wearing different disguises.
And that's what this is all about. You can see how all these famous hard problems, things like finding the optimal route for a delivery truck or scheduling exams, are all linked together. You can use that reduction trick we talked about to transform any one of them into any other. And what that means is, if you ever found a fast solution for just one of them, you would instantly have a fast solution for all of them, proving that P equals NP and probably collecting a $1 million prize in the process. So after all this deep dive into undecidability and crazy complexity classes, you might be asking yourself, okay, but why does any of this actually matter in the real world?
Well, it's actually incredibly practical. For one, it stops us from wasting years trying to solve a problem that's provably impossible. Instead, it pushes us to be smarter, to look for good enough solutions for things like logistics and scheduling. And here's a big one. It's the entire foundation of modern cryptography. The fact that some problems are super hard to solve is literally what keeps your bank account and your messages safe.
So in the end, understanding these limits isn't some kind of failure. It doesn't hold us back. What it really does is challenge us to be more ingenious, to think outside the box, and to invent completely new ways to tackle the world's hardest problems.
And that's the thought I want to leave you with. Knowing that these hard limits exist, what's the next problem that seems impossible today that we'll learn to solve tomorrow? Not by breaking the rules of computation, but by finding a brilliant new way to work around them.